The Incredible Universe Part 2. Mercury. The spacecraft Messenger found evidence of water ice on Mercury. There may be scientific support, based on studies reported in March 2020, for considering that parts of the planet Mercury may have been habitable, and perhaps that life forms, albeit likely primitive microorganisms, may have existed on the planet. Venus. In the early 20th century, Venus was considered to be similar to Earth for habitability, but observations since the beginning of the space age revealed that the Venusian surface temperature is around 467 degrees Celsius, 873 degrees Fahrenheit, making it inhospitable for Earth-like life. Likewise, the atmosphere of Venus is almost completely carbon dioxide, which can be toxic to Earth-like life. Between the altitudes of 50 and 65 kilometers, the pressure and temperature are Earth-like, and it may accommodate thermoacidophilic extremophile microorganisms in the acidic upper layers of the Venusian atmosphere. Furthermore, Venus likely had liquid water on its surface for at least a few million years after its formation. The putative detection of an absorption line of phosphine in Venus's atmosphere, with no known pathway for abiotic production, led to speculation in September 2020 that there could be extant life currently present in the atmosphere. Later research attributed the spectroscopic signal that was interpreted as phosphine to sulfur dioxide, or found that in fact there was no absorption line. The Moon. 3.5 to 4 billion years ago, the Moon could have had a magnetic field, an atmosphere, and liquid water sufficient to sustain life on its surface. Warm and pressurized regions in the Moon's interior might still contain liquid water. As of 2021, no native lunar life has been found, including any signs of life in the samples of moon rocks and soil. Mars. Life on Mars has been long speculated. Liquid water is widely thought to have existed on Mars in the past, and now can occasionally be found as low-volume liquid brines in shallow Martian soil. The origin of the potential biosignature of methane observed in the atmosphere of Mars is unexplained, although hypotheses not involving life have been proposed. There is evidence that Mars had a warmer and wetter past. Dried-up riverbeds, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found. Evidence obtained by the Curiosity rover studying Aeolus Palus, Gale crater in 2013 strongly suggests an ancient freshwater lake that could have been a hospitable environment for microbial life. Furthermore, present conditions on the subsurface of Mars may support life. Current studies on Mars by the Curiosity and Perseverance rovers are searching for evidence of ancient life, including a biosphere based on autotrophic, chemotrophic and/or chemolitho-autotrophic microorganisms, as well as ancient water, including fluvio-lacustrine environments, plains related to ancient rivers or lakes, that may have been habitable. The search for evidence of habitability, taphonomy, related to fossils, and organic carbon on Mars is now a primary NASA objective. Ceres. Ceres, the only dwarf planet in the asteroid belt, has a thin water vapor atmosphere. The vapor could have been produced by ice volcanoes or by ice near the surface sublimating, transforming from solid to gas. Nevertheless, the presence of water on Ceres had led to speculation that life may be possible there. It is one of the few places in the solar system where scientists would like to search for possible signs of life. Although the dwarf planet might not have living things today, there could be signs it harbored life in the past. Jupiter. Carl Sagan and others in the 1960s and 1970s computed conditions for hypothetical microorganisms living in the atmosphere of Jupiter. The intense radiation and other conditions, however, do not appear to permit encapsulation in molecular biochemistry, so life there is thought unlikely. In contrast, some of Jupiter's moons may have habitats capable of sustaining life. Scientists have indications that heated subsurface oceans of liquid water may exist deep under the crusts of the three outer Galilean moons, Europa, Ganymede, and Callisto. The EJSM Laplace mission was planned to determine the habitability of these environments. However, due to lack of funding, the program was not continued. Similar missions, like ESA's JUICE and NASA's Europa Clipper, are currently in development and are slated for launch in 2023 and 2024, respectively. Europa. Main article. Life on Europa. Internal structure of Europa. The blue represents a subsurface ocean. Hydrothermal vents on the bottom of the ocean, if they exist, may warm the water and could be capable of supplying nutrients and energy to microorganisms. It is also possible that Europa could support aerobic macrofauna using oxygen created by cosmic rays impacting its surface ice. Scientists found that ice shelves surrounding the lakes appear to be collapsing into them. thereby providing a mechanism through which life-forming chemicals created in sunlit areas on Europa's surface could be transferred to its interior. On the 11th of December 2013, NASA reported the detection of clay-like minerals, specifically phyllosilicates, often associated with organic materials, on the icy crust of Europa. The presence of the minerals may have been the result of a collision with an asteroid or comet, according to the scientists. The Europa Clipper, which would assess the habitability of Europa, is planned for launch in 2024. Europa's subsurface ocean is considered the best target for the discovery of life. Saturn system. Like Jupiter, Saturn is not likely to host life. However, its moons Titan and Enceladus have been speculated to have possible habitats supportive of life. Enceladus. Enceladus, a moon of Saturn, has some of the conditions for life, including geothermal activity and water vapor, as well as possible under ice oceans heated by tidal effects. The Cassini-Huygens probe detected carbon, hydrogen, nitrogen and oxygen, all key elements for supporting life, during its 2005 flyby through one of Enceladus's geysers spewing ice and gas. The temperature and density of the plumes indicate a warmer, watery source beneath the surface. Of the bodies on which life is possible, living organisms could most easily enter the other bodies of the solar system from Enceladus. Titan. Titan, the largest moon of Saturn, is the only known moon in the solar system with a significant atmosphere. Data from the Cassini-Huygens mission refuted the hypothesis of a global hydrocarbon ocean, but later demonstrated the existence of liquid hydrocarbon lakes in the polar regions, the first stable bodies of surface liquid discovered outside Earth. Analysis of data from the mission has uncovered aspects of atmospheric chemistry near the surface that are consistent with, but do not prove, the hypothesis that organisms there, if present, could be consuming hydrogen, acetylene and ethane, and producing methane. NASA's Dragonfly mission is slated to land on Titan in the mid-2030s with a VTOL-capable rotorcraft with a launch date set for 2027. Other bodies. Models of heat retention and heating via radioactive decay in smaller icy solar system bodies suggest that Rhea, Titania, Oberon, Triton, Pluto, Eris, Sedna, and Orcus may have oceans underneath solid icy crusts approximately 100 kilometers thick. Of particular interest in these cases is the fact that the models indicate that the liquid layers are in direct contact with the rocky core, which allows efficient mixing of minerals and salts into the water. This is in contrast with the oceans that may be inside larger icy satellites like Ganymede, Callisto, or Titan, where layers of high-pressure phases of ice are thought to underlie the liquid water layer. Hydrogen sulfide has been proposed as a hypothetical solvent for life and is quite plentiful on Jupiter's moon Io, and may be in liquid form a short distance below the surface. Scientific search. The scientific search for extraterrestrial life is being carried out both directly and indirectly. As of September 2017, 3,667 exoplanets in 2,747 systems have been identified, and other planets and moons in the solar system hold the potential for hosting primitive life such as microorganisms. As of the 8th of February 2021, an updated status of studies considering the possible detection of lifeforms on Venus, via phosphine, and Mars, via methane, was reported. Direct search. Lifeforms produce a variety of biosignatures that may be detectable by telescopes. Scientists search for biosignatures within the solar system by studying planetary surfaces and examining meteorites. Some claim to have identified evidence that microbial life has existed on Mars. An experiment on the two Viking Mars landers reported gas emissions from heated Martian soil samples that some scientists argue were consistent with the presence of living microorganisms. Lack of corroborating evidence from other experiments on the same samples suggests that a non-biological reaction is a more likely hypothesis. In 1996, a controversial report stated that structures resembling nanobacteria were discovered in a meteorite, ALH 84001, formed of rock ejected from Mars. Electron micrograph of Martian meteorite ALH 84001 showing structures that some scientists think could be fossilized bacteria-like life forms. In February 2005, NASA scientists reported they may have found some evidence of extraterrestrial life on Mars. The two scientists, Carol Stoker and Larry Lemke of NASA's Ames Research Center, based their claim on methane signatures found in Mars's atmosphere resembling the methane production of some forms of primitive life on Earth, as well as on their own study of primitive life near the Rio Tinto River in Spain. NASA officials soon distanced NASA from the scientists' claims, and Stoker herself backed off from her initial assertions. Though such methane findings are still debated, Support among some scientists for the existence of life on Mars exists. In November 2011, NASA launched the Mars Science Laboratory that landed the Curiosity rover on Mars. It is designed to assess the past and present habitability on Mars using a variety of scientific instruments. The rover landed on Mars at Gale Crater in August 2012. The Gaia hypothesis stipulates that any planet with a robust population of life will have an atmosphere in chemical disequilibrium, which is relatively easy to determine from a distance by spectroscopy. However, significant advances in the ability to find and resolve light from smaller rocky worlds near their stars are necessary before such spectroscopic methods can be used to analyze extrasolar planets. To that effect, the Carl Sagan Institute was founded in 2014 and is dedicated to the atmospheric characterization of exoplanets in circumstellar habitable zones. Planetary spectroscopic data will be obtained from telescopes like WFIRST and ELT. The Green Bank Telescope is one of the radio telescopes used by the Breakthrough Listen project to search for alien communications. In August 2011, findings by NASA, based on studies of meteorites found on Earth, suggest DNA and RNA components, adenine, guanine and related organic molecules, building blocks for life as we know it, may be formed extraterrestrially in outer space. In October 2011, scientists reported that cosmic dust contains complex organic matter, amorphous organic solids with a mixed aromatic aliphatic structure, that could be created naturally, and rapidly, by stars. One of the scientists suggested that these compounds may have been related to the development of life on Earth and said that, if this is the case, life on Earth may have had an easier time getting started as these organics can serve as basic ingredients for life. In August 2012, and in a world first, astronomers at Copenhagen University reported the detection of a specific sugar molecule, glycolaldehyde, in a distant star system. The molecule was found around the protostellar binary IRAS 16293-2422, which is located 400 light-years from Earth. Glycolaldehyde is needed to form ribonucleic acid, or RNA, which is similar in function to DNA. This finding suggests that complex organic molecules may form in stellar systems prior to the formation of planets, eventually arriving on young planets early in their formation. Indirect search. Projects such as SETI are monitoring the galaxy for electromagnetic interstellar communications from civilizations on other worlds. If there is an advanced extraterrestrial civilization, there is no guarantee that it is transmitting radio communications in the direction of Earth or that this information could be interpreted as such by humans. The length of time required for a signal to travel across the vastness of space means that any signal detected would come from the distant past. The presence of heavy elements in a star's light spectrum is another potential biosignature. Such elements would, in theory, be found if the star were being used as an incinerator, repository for nuclear waste products. Extrasolar planets. Artists' impression of Gliese 581c, the first terrestrial extrasolar planet discovered within its star's habitable zone. Some astronomers search for extrasolar planets that may be conducive to life, narrowing the search to terrestrial planets within the habitable zones of their stars. Since 1992, over 4,000 exoplanets have been discovered, 5,307 planets in 3,910 planetary systems including 853 multiple planetary systems as of the 1st of February 2023. The extrasolar planets so far discovered range in size from that of terrestrial planets similar to Earth's size to that of gas giants larger than Jupiter. The number of observed exoplanets is expected to increase greatly in the coming years. Thanks for watching. Please like and subscribe.